We talked about the rules which are written on there. Let's go through an example and talk about a method that you can use. Now, you can always kind of what I call guess and check, just change numbers around until it fits. And that's fine if that's what works for you, but systematic approach is sometimes a little bit easier. So I'm going to use the first equation on here as an example as I do this. All right, so the first thing you want to do is you want to decide what elements you're going to look at first. And it's important to see if there are ones that are not a good idea to start with. So there are two things that make elements hard to start with. One is if the element appears in more than one chemical on the same side. And that's because if you change one, you're not changing all of them. So you kind of want to save those until the end. Hope that they balance out when you're balancing other things. Save for last. Elements that appear twice on one side. Now everything's going to appear at least twice because it'll be at least in the reactants and the products once. So you're just looking at one side. So oxygen appears in the product side twice there. We also want to save for the last pure elements. And in this case, oxygen fits the bill again. And the reason for that is that when you change a pure element, you're not changing anything else. So if that's the last thing you balance, then you don't have to go back and fix other things that have changed along the way. So you're going to look at the equation, see if that applies to anything and say, okay, I'm not going to start with those. I'm going to start with something else. So kind of the definition of balancing, but I'll just throw this in here just as a reminder that this is what the process is. I think you kind of get this, is that for each element, we're going to in turn try and figure out whether or not we have the same on each side. So if we look at carbon, we can see, okay, there's one carbon, we're good. But if they're not, remember the only thing we're allowed to do is change the coefficient. So the coefficient is the big number out front, and the coefficient applies to the whole molecule. Now, when I change the coefficient, I'm not adding molecules, I am multiplying. So if I change this to a 2, it's not that I'm going from 1 to 3 because I added 2. I'm just changing it to 2. I'm multiplying 1 times 2. Okay, so one molecule twice. Okay. So if not, we're going to change one coefficient so the number of atoms matches. Okay. So we didn't have to do anything with carbon. So we'll look at hydrogen next. So here I have 4, and over here I only have 2. Now, for some people, it's helpful to visualize this. So if I think of this as a molecule, I'm going to use carbon as an open circle, and hydrogen is little tiny dots. That's one of those. Right now I'm going to do a line through oxygen. I have one water molecule. So one water molecule only gives me 2 of these. So how many water molecules do I need? So now I can count. I have 1, 2, 3, 4 hydrogens. 1, 2, 3, 4 hydrogens. Every time you do this, unless you've just balanced an element, it's going to lead you to a new one that you're going to balance. So I've just changed my number of oxygens. That's probably the next thing that I should balance. So you're going to go along. You're going to do all of these. And then once you get to the end, well, let's finish balancing first. So now I have this. So on this side, I have 1, 2, 3, 4 hydrogens, 1, 2, 4 hydrogens on the product side. Reactant side, I have 1 carbon. Product side, I have 1 carbon. Product side, I have 1, 2, 3, 4 oxygens. This is just 2 oxygen atoms. So how many oxygen molecules do I need in order to balance that out? I need 2. Oh, and I needed to put a 2 up here, didn't I? You guys got to tell me when I forget to do this. Okay, so yeah, I'm going to need a 2 here. Okay, so if you do it visually like this, then you can kind of physically count them. Some people will do that by just writing the letters, and that's fine as well. Once you have done this, you want to make sure, because you're constantly changing elements from side to side, the more complex this gets, you want to go back and recount your atoms on both sides. What I like to do is draw a line from the arrow so I can keep my products and my reactants separate. And then I'm going to skip 3 because we're going to come back to 3 in just a second. 4, you're going to count atoms on both sides to verify. This one's not too hard. It was a little harder than the one we did Wednesday. But sometimes we run into what I call an even-odd conflict. So we're going to look at an example where it looks almost like this. I'm just going to change one chemical. And when I change that chemical, it's going to make this a lot harder to balance. So as I'm going through here, I'm going to notice right away that I'm going to need 2 carbon dioxides, right? I'm saving my oxygen for last because it appears twice in the products and it also appears as a full element. Then I'm going to go to my hydrogens. I have 6 hydrogens here. So what does this coefficient need to be? How am I going to get 6 hydrogens on my product side? Well, if I put a 6 here, then I'll have 6 water molecules. And if I have 6 water molecules, I'd have 12. So I want 3. Yeah. Okay, so this is 3 of those molecules. So when you want to check, you're going to multiply the big number by the small number. So 2 times the invisible 1 is 2 carbons. 2 times the little 2 is 4 oxygens. 3 times the little 2 is 6 hydrogens. 3 times the invisible 1 is 3 oxygens.
Or you have an odd number of oxygen on the right side, so that
and that's the even-odd conflict.
Multiply it by 2.
Okay, so you're jumping ahead. So first of all, if you have an even-odd conflict, and let me point out why this is a problem. The only way I can balance my oxygens over here is with this. And no matter what number I multiply this by, since I'm multiplying by 2, I'm always going to have an even number. I can't get an odd number of oxygens on this side. Okay, so that's why I have an even-odd conflict, is right now I have an odd number of oxygens, and I can only get even over here. So when you have an even-odd conflict, you're going to multiply by 2. Now, just the ones you've already changed, because you haven't really looked at the others yet. Okay? So I've recognized I have a problem. I'm going to go back to the beginning, and I had addressed this, so I didn't change it, but I did look at this molecule. So I'm going to call that 2. I'm going to call this 4 and this 6. Okay, doing that makes me have an even number on the other side, but also keeps everything else balanced. And I can double check that. So I've got 2 times 2 is 4 and 4 carbons. I have 2 times 6 is 12 hydrogens. 6 times 2 is 12 hydrogens. So now we're back to, I don't know who said it before, but we said 6 waters, and it turned out that actually was right. So we have 4 carbons. We have 4 times 2 is 8 oxygens. We have 6 times 2 is 12 hydrogens. And then we also have 6 oxygens. So that makes 14 oxygens on this side. Over here we have 2 times 2 is 4 carbons. And then we have 2 times 6 is 12 hydrogens. So those are good. But now I need to fix my oxygens. So since I have 14 on this side, atoms of oxygen, how many molecules of oxygen do I need over here? I need 7. Okay, so now 7 times 2 is 14 oxygen. Then we can, I've gone through and checked carbon and hydrogen. My oxygen is 7 times 2 is 14. And over here I have 14. So I verified my amount. Okay, that's our basic idea. So what I'd like you to do, give the next few ones a try. When you get to the one that is 4th, they're not numbered. Remember, that is a structural formula. So you have to count up the carbons. They're not all grouped together. So it's actually 2 carbons and 6 hydrogens in that one molecule. So sometimes they're written out like that. You want to make sure you can count those. So give that a try for a few minutes, see what you get. Don't worry about the charges for right now. We'll get to those later. Right now, we're just looking at atoms.